The purpose of this video is basically to supplement the last part of the lecture that we just didn't get enough time to do yesterday, and that is covering the properties of alkanes, which would kind of close out that first part of the chapter and leave us with kind of working with some other derivatives and things in our lectures next week. So I just wanted to kind of close this out. There really aren't a whole lot of questions about this kind of material in the post-lecture assignment, but there was one, and I wanted to identify it and kind of just point it out to you, just so you have a way of kind of doing it and not running into as many problems with it. So just looking at this here, if we're talking about alkanes, and again, we're getting into kind of the physical and chemical properties. We spent most of our time in our last lecture looking at nomenclature and kind of what the differences between hydrocarbons and inorganic materials were. What we're going to look at here is just kind of some more general physical properties overall. And so for that, we kind of have to get into, well, what are alkanes used for? And so what we use them for really has to do a lot with what the chemical formula is. So if I've got an alkane that has between 1 and 4 carbons, most of these are gases at room temperature. Butane kind of draws that line between gas and liquid. If we introduce just a little bit of pressure to it, it liquefies pretty easily. Their primary use, we burn them. They heat. So methane, natural gas, gets used for heating homes, for use in things like gas stoves. Propane is also a home heating element in some cases. It's also a cooking heat element in some cases. Butane has some of that same kind of utility as well. We tend to see it more in kind of torches or handheld lighters, those kinds of things. At 5 to 8 carbons, we're talking about primarily liquids. These liquids are highly volatile. And so again, we need to really make sure we understand our terms here. That means that they turn to gas easily. And we want to separate that from flammability. Flammability is, the ability to burn in the air. And while these are also flammable, volatility does not necessarily mean flammability. The two are different things, but oftentimes they are combined because a lot of times things that are flammable are also volatile at the same time. At carbon chain length 9 through 17, these are liquids. Also, they have higher boiling points, and so they tend to be a little bit more stable at room temperature, but they are also volatile enough that we can burn them without a whole lot of effort on our parts. And so we find these things like motor oil, mineral oil, kerosene, diesel, jet fuel, things that we know burn, but generally require a little bit more energy to actually get the burning process started. At 18 or more atoms, this is where we start to kind of venture into the solid phase. This group of compounds is collectively known as paraffins. Paraffins, you may have heard of paraffin wax. The reason why that is a thing is because those paraffins tend to have a waxy kind of exterior. They tend to be waxy kinds of compounds. And then just as kind of a common example, petroleum jelly, otherwise known by its brand name Vaseline. Here you have a semi-solid mixture. Especially when you first open it up, it appears to be solid, but it's kind of got this goopy texture to it. Over time, you will see that semi-solid nature does start to separate. You do see some, small pools of oil forming in the petroleum jelly over time, but you've got a mixture of hydrocarbons in that. And those hydrocarbons generally have 25 or more carbon atoms in the chain. What do we know about alkanes? Well, we just described a whole bunch of oils and fuels. And one of the things that we definitely know about those, they are insoluble in water. And we also know that they are less dense than water because we know that they float, which is why when you have something like this, where we've got an oil spill out in the middle of what's probably the Gulf of Mexico here, you've got that oil that sits on the top, and it'd be really hard to remove from the ocean because even though it sits on the top, it starts to get dispersed, it starts to get churned up. We have a really hard time getting all of it, and certainly have a hard time getting all of it before it starts to affect aquatic life. Alkanes themselves, in addition to this solubility and this density thing, we know that they are nonpolar. And we know this because their insolubility, there's an expression in solubility, like dissolves like. Polar and nonpolar substances don't mix. They aren't alike. They are different. We also know alkanes to be flammable in air, and crude oil is a combination of many alkanes. The last thing that we want to know out of this particular section is about these combustion reactions. So combustion is just a way of saying burning reactions. So when alkanes burn, what happens? Well, what happens is the oxygen in the air is going to react with the different components of the alkane. And so we have to remember that alkanes are carbon and hydrogen primarily. The carbon, when it reacts with oxygen, would create carbon dioxide. The hydrogen, when it reacts with oxygen, is going to make water. And so when we do these kinds of chemical reactions between alkanes and oxygen, these combustion reactions, carbon dioxide and water are going to be the primary products. Now, if we have a substituted alkane, one that's got a halogen in it or one that's got another element in it, then we might see some additional side products kind of make their way out of this. And those tend to have a lot more complicated kinds of chemistries, and they also tend to be a whole lot more dangerous in terms of their burning capabilities, and what happens, what kinds of products they form when they burn. So the net result here is we're going to get a whole heck of a lot of energy related to these. And we're going to change some of the language here because this isn't quite correct. Chemical reactions are always this interplay and balance of energy. It takes energy to break a bond. It always takes energy to break a bond because we have to think about we're overcoming the attractive forces that exist between those two atoms. And so if I was going to try to separate your fingers when they are interlocked, it's going to require a bit of energy to break those apart. And the same is true for chemical reactions for slightly different reason. The attractive forces have to be overcome to break that bond. Now, that being said, when those attractive forces are overcome and that bond is broken, now you've got these reactive elements walking their way around through the air, and they're going to react with whatever's around. And whatever's around, usually in this case, is oxygen. And so those oxygen atoms are going to form new bonds in the process, new bonds with carbon, new bonds with hydrogen. And the net result is, as those new bonds are made, the energy that went into breaking those bonds gets released in the form of these new bonds being made. And the reason why we get so much energy out of these reactions is that the energy it took to break these bonds is less than the energy that is given off when these new bonds are made. But we will always see in combustion reactions high amounts of energy taking place. And that's why we get heat, light, in some cases sound, when it comes to burning hydrocarbons. So before we break this off here, I just wanted to show this kind of reaction did show up in one of the homework problems. And not only did it show up, it wanted you to balance said equation. And there's a problem with that because we haven't really talked about balancing equations in any kind of way. And it's really not our place to do so for this course. While we are interested in the chemistry and things that are happening, we really don't want to get bogged down with kind of the nuts and bolts of the process here. And so anytime we come across chemical equations, we usually talk about them from kind of a perspective of this is what happens, and not so much the kind of arithmetic behind how many atoms of each kind there are. And so I did want to draw your attention. This is the last question in your analysis, in your post-lecture here. And for the most part, it's relatively straightforward. It's a lot like the other questions that are in the assignment, with one really important part and difference. This last part here. Enter the balanced chemical equation for the complete combustion of nonane. Now, what they are looking for is they are looking for you to take your reaction between nonane, which we can establish as C9H20, based upon what we talked about yesterday. And the reason this is getting marked wrong is it wants the condensed structural formula instead of the actual formula. So that would bog us down a little bit more. We would have to put in CH3, CH2, 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 4. There's 5 carbons, 6 carbons, 7 carbons, 8 carbons, 9 carbons. And then we've got to do the formatting that it likes too. And now it says that we're okay. C9H20 was the formula, but it was looking for this. Drawing, you saw that in a number of other examples. That should be okay. Solid, liquid, or gas, based upon its temperature, you should be able to answer that. Is it soluble in water? It's a hydrocarbon, so no. Will it float or sink? Going back to the stuff we just talked about, it'll float. What is the balanced chemical equation? Well, this is what we're talking about. They want C9H20 plus oxygen makes CO2 and H2O. And not only do they want all of that, but they also want you to put in the phases of matter, which is, we know this is a liquid. Oxygen is a gas. Carbon dioxide is a gas. And water, when it comes to combustion reactions, is also a gas. So now I've got this, but again, that's not good enough because it's not balanced. And so what I would direct you toward here, again, since we're not trying to balance, is I would be directing you toward another tool. And the tool I would introduce you to here is this tool that I'm putting up on the screen now. This is just simply an equation balancing tool. And what you can do with it is, if you have kind of the nuts and bolts of the equation, you can put it in here, and it's going to yell at you for some of that. So C9H20 plus oxygen equals CO2 plus H2O. And if you hit the balance button here, it'll tell you what the correct coefficients are. And you could put those in here, 14, 9, 10. And now it's going to tell you that you did it correctly. So here's the thing. You can do all that. But you should also know that I went into mastering. I saw some of the early feedback on this from the assignment. I went back into mastering. I gave everybody full credit for that part of the question. So you can do it if you want. You don't have to do it. It should be marked as full credit either way. So that's where we're going to stop here, just to kind of look ahead now. So looking ahead to our next lecture, we're going to go from alkanes, where we had just single bonds everywhere, to now we're going to go to a derivative of those, the alkenes and the alkynes, where we have double bonds and triple bonds between carbons being introduced. And so that'll add, again, just that next little layer of complexity to our discussion of organic chemistry. But we should be okay to kind of add that if we've done our good practice this weekend. So with that, I will end the video here. Have a great weekend, and I will see you next time.